Bonjour à tous. Welcome everyone to this webinar unlocking the full potential of wind propulsion of maritime decarbonization. So I'm Aude Leblanc. I am technology leader for sustainable shipping at Bureau Veritas. And today I am pleased to be your moderator and speaker for this webinar. I come with our panel of experts. So Mr. Robert Elliott. So Robert is a global market leader for tanker at Bureau Veritas commercial team, and Mr. Johan Le Gonigdet. Johan is the head of the Maritime Energy Transition Advisory at Bureau Veritas Solutions, Marine and Offshore in France. So today, our goals are to gain a comprehensive overview of the regulatory landscape and the technical expertise to guide the implementation of wind propulsion technology. So first, we will dive into regulatory landscape, navigating the IMO strategy and European Fit for 55 package of regulations applicable to maritime energy transitions. So then we will discuss safe adoption of wind propulsion on the market. And finally, we will highlight some guide and support provided by Bureau Veritas Solutions for wind propulsion adoption. So before we start, just an information. So you will be able to ask us some questions. So please post your question in the Q&A box on the top right-hand side of your clips. So you have to click on the Q&A, otherwise it goes only into the chats. So we will try to answer your question live, and for those that are not receive an answer, we will come back later to you. So now let's begin by investigate the regulatory landscape impacted by wind propulsion. And there is numbers of local regulatory frameworks addressing ship energy transition. Here I will focus on the main packages, which are the IMO, International Maritime Organization, and the European one. So globally, the IMO has set an ambitious target for achieving net zero GHG emissions by 2050. Meanwhile, the European Union also declared its ambition to become the first carbon neutral continent by 2050. So these objectives are supported by various regulatory measures that recognize wind propulsion technology as a viable solution for reducing emissions. So let's first take a look at the IMO GHG strategy. So as I mentioned earlier, the IMO has laid a clear pathway towards zero emission shipping through its revised GHG strategy adopted in 2023. So the basis of this strategy is a commitment to achieve net zero GHG emission from international shipping by or around 2050. This aligns the maritime sector more closely with the goals of the Paris agreements. So wind technology as a technology which reduces fuels need has a significant role to play. So to reach these long-term objectives, the IMO has set a series of intermediate milestones, as you can see here in the figures. It is interesting to see that the first steps aim to encourage the use of technologies that emits near zero or near zero greenhouse gas to at least 5%, with a goal of 10% of the energy used in shippings. So this represents an opportunity for wind propulsions. So now we will see how it is implemented into the IMO measures. So actually, IMO framework is based mainly on a tank-to-wake approach. So the consequence for the wind propulsion is that it is mainly based on the contribution of the wind propulsion as an energy efficiency device, allowing reduction of fuel consumptions. So it is the strategy is divided into design and technical measures, with the EEDI, Energy Efficiency Design Index, and EXI, Energy Efficiency Existing Ship Index, and also operational measure with the CRI, Carbon Intensity Indicator. So I will describe them later in these presentations. So these measures are all including in the annex of the Prevention of Air Pollution from Ships to the International Convention of the Prevention of Pollution from Ships, so the MARPOL Annex 6. There is a third measure which has been approved during the last MEPC in April this year. So the the fuel intensity mechanism, a mechanism which is based on the Marine fuel standard and GHG emission pricing for shipping. So this first measure is based on a well-to-wake approach. This means that it doesn't limit to the emission to just those produced by onboard consumption. It also includes emission from the energy production used. So this represents also an opportunity to consider emission-free benefits from wind energy. So what about the design measure, the EEDI and EEXI? So EEDI and EEXI are already well-known metrics today. This index measures the gram of CO2 emitted by ships' capacity miles. The goal of this measure is to enhance the technical performance of ships and to support the adoption of more energy-efficient equipment. And wind propulsion is one of them. So lower EEDI indicates that a more energy-efficient ship design. It provides a specific figure for individual ship design and is calculated by a formula based on the technical design parameter for given ships. Indeed, as you can see in this figure, EEXI EEDI accounts for engine and auxiliary engine power, auxiliary and main engine savings, so including saving from wind propulsion, and transport capacity. So emissions are calculated using the installed power of the engine, specific fuel oil consumption, and the conversion factor of the fuel mass into CO2 mass. So EEDI requirements become progressively stricter over time, and the current phase 3, which the most ships started in 2025, require new vessels to be approximately 30% more efficient than the EEDI reference line. This could be challenging for some ship types, and wind propulsion could be a viable solution to comply with. So it's a one-time certification. So concerning retrofit to install a wind propulsion, as it is not considered major conversion, there is no need for recertification of EEDI. However, and I will address this later in the discussion, you will see that reward factor considered in the FuelEU Maritime regulations refer to the methodology for calculation of the contribution of wind propulsion in the EEDI technical file. So it may still be interesting to reconsider a recertification to take into account the contribution of wind propulsion, so it is on a voluntary basis. So now, to go into the detail for the EEDI calculation, on this slide, you can see a big formula. So what I want to show you here is the way how wind propulsion impacts the calculations. So as I have mentioned just before, the wind propulsion contributes to a main engine savings device by deducing the available effective power of wind propulsion to the main engine power. So I want also to highlight that wind propulsion can reduce deadweight capacity here due to increased lightweight. And this is impact EEDI, EEXI calculations. Even so, generally, it's a minor effect. So concerning calculation of the effective power of wind propulsion, it is provided into the IMO guidance, circular 896, and it defines calculation of the wind propulsion power, the power consumption of wind propulsion systems that need to be added. And we also note that by sorting the first element in descending order and the wind probability to reduce to the half with the best performance, it is a form of weather routing. So it considers that the ship will reach wind conditions that are suitable for the wind propulsion system. And this method is debatable today. It is also worth to note that the guidance requires no specific sea trials to validate the EEDI with wind propulsion calculations. So the effect of wind propulsion can be determined with certainty early in the project and don't need any sea trials validations. So the calculations involve complex matrices. So it includes a force matrix, which can be determined on wind tunnel model test, of CFD or full-scale test. It is provided by the wind propulsion provider. It's involved also a power consumption matrix, also provided by the wind propulsion provider, and the wind probability on global truth matrix. This is given by and defined by the IMO guidance 896. So all of these matrices are given according to wind direction and wind speed, with 5 degree steps for wind angle and 1 meter per second step for true wind speed, from 1 to 25 meter per second. So it is worth to note that the result of this calculations method may differ from actual prediction. It is because only one ship speed is used, the reference speed of the ship, and not the operational speed profiles. So the ship drive is also usually at the maximum summer load, and the route optimization is not really considered. So we have seen that it is considered the half-best performance with the good condition of wind. And the local wind condition for the specific troops are not a confirm. So because we consider here a global route and not a specific route. So that's why I don't recommend to use this EED result to predict savings for specific routes on ships. So this approach has the advantage to define a calculation method, and it is possible to make some relative comparison of different wind propulsion arrangements, and particularly the number of wind propulsion systems. It is also important to note that the first matrix itself is then validated by the verifier, and it can be used for further analysis, for example, to assess expected savings from the different operational profiles. So the EDI was about design measures. So now we'll talk about operational measures. So specifically, the carbon intensity indicator, CRI. It is based on the annual CO2 emission per capacity nautic mile, same as EDI EXI, but it is calculated from actual consumed fuel and travel distance. It determines the annual factor needed to ensure continuous improvement of ship's operation carbon intensity within a specific rating level. So the installation of wind propulsion is a valid measure to be listed in the corrective action plan if the attempt CRI is below the required CRI. However, there is no special consideration or formula for wind propulsion technologies under the CRI. So the impact of wind propulsion is mainly indirect, as it is based on fuel savings. It is good also to note that, however, that a percentage of fuel savings is different than the percentage of improvement in CRI, because the CRI, the wind propulsion only makes saving when the ship is underway with sufficient winds, while the CRI includes also at berth and generator consumptions. So now to finish about the IMO framework. So the IMO is also developing a well-to-wake regulation named GHG fuel intensity, GFI. So it's a combination of emission limits and prices mechanism for emissions. So wind propulsion will impact the GFI based on the amount of fuel saved. But here the change is that the wind is recognized as a zero-rated fuels. So wind energy delivered by the wind propulsion system is recognized as energy in the same context as other fuels. So therefore, wind propulsion contributes to the amount of energy used by the ships. So the emission-free energy of wind can reveal its full benefits here. So this measure will set to be formally adopted in October 2025 before entry into force in 2027. And it is also good to note that there is a need to clearly define the calculation of the energy coming from wind propulsion, and there is a lot of discussion about this subject. So now let's look at the European framework. So Europe has declared its ambition to become first carbon neutral continent by 2050, and they set different steps for reducing the GHG intensity of ships in Europe. So the different European measures are given into the Fit for 55 package, which is a set of regulations to reduce the EU emission by at least 55% by 2030. For ships, and in particular wind propulsion, the FuelEU Maritime and the EU ETS are of particular interest. They are both regulatory frameworks designed to reduce greenhouse gas emissions in the maritime sector, but they operate in a distinct ways. So FuelEU Maritime focus on setting limits on the GHG intensity of energy use on board ships. This means that the ships have to reduce their emission per unit of energy consumed. It is based on a well-to-wake approach and not restricted to CO2, but includes methane and nitrous oxide emission as well. So ship owners are required to pay penalty for every ton of CO2 equivalent emitted in excess to the target. The requirements will become more stringent every 5 years. Contrary, EU ETS is a cap-and-trade system that places a cap on the total amount of GHG emissions allowed within the Europe. So companies are allocated emissions allowance, which they can then trade. If a company exceeds its emissions limits, it must purchase additional allowance, which can become more expensive over time. So in this framework, we see the importance of limiting emissions to avoid penalty or the need to purchase emissions allowance. This represents an opportunity for wind propulsion and its role in reducing fuel consumptions, thereby limiting emissions. So let's focus on the FuelEU Maritime initiative. So this initiative aims to promote the use of renewable, low-carbon fuel and clean energy technology for ships, such as wind propulsions. So reducing fuel consumption will directly reduce the penalties if there is a compliance deficit. Therefore, one of the effects of wind propulsion is FuelEU is a reduction of fuel consumption. But additionally, an incentive for wind propulsion is including. So a reward factor is incorporated in the calculations and allow wind to improve the GHG intensity depending on the amount of wind power installed. So the reward factor is determined from the ratio of the power provided by the wind propulsion system compared to the installed propulsion power. So these power values are calculated in accordance with the IMO guideline for the energy efficiency design index, circular 896, I just mentioned previously for the EEDI calculations. So to be eligible for the reward factor, the EEDI EXI technical file should be updated and verified to include the calculation of wind propulsion contributions. So it is also important to note that in case of mid-year installations, the same reward factor is applied for the entire year. So for a retrofit of the wind propulsion system at the end of the year, it allows the application of reward factor for the entire year. So now let's dive into practical example to illustrate how wind propulsion can impact compliance and penalty under the FuelEU Maritime regulations. So here some example. The example in the first scenario, we have a wind propulsion system with power output of 900 kilowatts and the main propulsion power of 7,000 kilowatts. It gives a reward factor of 0.97. And it means that the compliance balance improved by more than 1,000 tons CO2 equivalent. And so the penalty are completely eliminated, achieving a reduction of 100%. So for example 2, in this scenario, the wind propulsion system is operational for the full report period with a power output of more than 1,000 kilowatts, and the main propulsion power is more than 6,000 kilowatts. So the reward factor, we get 0.95, and it proving the emission by more than 2,000 tons of CO2 equivalents. So the penalty here are also completely eliminated. For the example 3, the main propulsion power is 7,000 kilowatts, and the wind propulsion power is 400 kilowatts. So we get a reward factor of 1.99, and it's improve the emission by more than 500 tons CO2 equivalent. So the penalty are not totally eliminated, but are reduced by 43%, equating a savings of 452 euros. So this example demonstrates that it is possible to eliminate partially or totally the penalty when considering wind propulsion installations. So another regulatory frame for European emission reduction is the EU ETS, so emission trading systems. There is no special consideration for wind propulsion under these mechanisms, but wind propulsion will impact indirectly based on the fuel savings. For example, with an allowance at 75 tons per ton of CO2 equivalent, each ton of fuel saved equates to approximately 300 euros in avoided EUR cost. So with the example presented in the previous slides, we see that the cost saved according to fuel saving from wind propulsion are between 41 kilo euros to 175 kilo euros. So to finish on the regulatory landscape, I hope that you have noticed that the IMO GIG fuel intensity GFI mechanisms present very similar figures to the European regulations in terms of methodology and trajectory. So the economic element of the IMO measure can be compared with those with the Maritime EU ETS. This raises the question of what consequences this comparison might have for European regulation, alignment, or articulation. So according to the EU regulation here, so the Commission will examine any global IMO measure regarding its alignment with EU objective and consider possible articulation or alignment to avoid duplicating regulations. So now let's pivot to the market side of things. So we have explored how this regulatory framework translates into practical adoptions. So now joining me is Robert, so my colleague, global market leader for tanker ships, who will provide insight with the rapidly evolving field of wind propulsion adoptions. So now, Robert, good morning. So you're on mute.
Good morning, Lord. I'm pleased to be joining here today. I'm thrilled to join to discuss the complex regulatory landscapes and, of course, hopefully provide operational insights into wind propulsion technologies.
So yeah, I particularly invite you because we have seen that tanker at the forefront of wind propulsion adoptions. So this technology has rapidly evolved from concept to operational reality, with over more than 65 ships now equipped with wind propulsion systems, and tankers represent a significant portion of these new adopters. So what key factors are driving tanker operators to embrace this technology?
Yeah, the industry is now more confident in wind, and we're seeing that wind propulsion is feasible. There is still some hesitation, but it is rapidly changing. So the three main factors in driving adoption. Firstly, the regulatory framework, as you've explained, EU ETS, Fuel and Maritime, with its fixed incentives and reward factor, IMO's EEDI, EXI, CI, pushing ship owners to cleaner technologies, and and we're optimistic that IMO's net zero framework will further support the return on investment. Secondly, economic considerations. Wind propulsion offers fuel savings, and that's increasingly valuable as alternative fuels are considerably more costly than the fossil fuel counterparts. Thirdly, charterers are increasing focus on their Scope 3 emissions and demanding greener shipping solutions. And of course, we are seeing that charterers are further including and specifying wind propulsion in their specifications or their time charter requirements.
And can you elaborate on the economic benefits?
Yes, Ord. Wind propulsion can reduce fuel consumption from 5 to 20%. We've seen cases above, but we can take this as an average. This, of course, depending on routes, conditions, and applications. And this, of course, translating to significant cost savings. For tankers on long-term charters, these efficiency improvements are highly valued by the charterer, if the vessels are applied to the more beneficial routes, of course. And once again, the increased transition to more expensive alternative fuels, wind propulsion becomes an even more attractive solution to overcome these additional fuel costs.
And how do upcoming regulations impact this outlook?
Well, the proposed greenhouse gas pricing mechanism will strengthen the business case considerably. Depending on fuel strategy of the ship owners and the operator to stay compliant, the ROI will be considerably reduced depending on which fuel is selected. While the ROI for wind propulsion has decreased over the past decade, these regulations will likely shorten payback times to below 4 years in the medium term, and in the more long term, beyond 2035, we could see even shorter payback times. And this is, of course, due to increased fuel costs and the application of more expensive fuels. Unlike alternative fuels, wind systems are predictable in installation. Maintenance costs are rather fixed. So from an operational perspective, the OPEX can be predicted within the business case.
So speaking of cost, how do wind propulsion systems compare to transition to low carbon fuels?
Well, Ord, they are complementary strategies rather than alternatives. Wind systems require upfront investment, but are predictable. So the costs are predictable. The alternative fuels pricing and availability still remain uncertain, even though we see infrastructure developing and more investment in alternative fuels. Importantly, reducing fuel consumption once again via wind propulsion makes the transition to higher priced, low greenhouse fuels more economically viable. Even a 10% reduction can significantly improve the business case. The wind propulsion system strategy can be phased in. We can see that the initial capex or the initial design of 4 cells from new construction, when initial 2 cells can be installed to reduce initial capex, and at a later stage, the additional 2 cells can be installed after the first 5 years, as the first sales have proven the business case. This, of course, avoids high initial capex.
So regulatory compliance regarding emissions is essential. So we have seen that, but vessel safety remains also paramount. So at BV, we have developed some comprehensive technical rules to address wind propulsion challenges. Notation wind propulsion includes, for example, the detailed stability assessment, structural analysis, risk assessment, identify critical situation, requires specific operational responses. So this assessment often defines operational limits for wind propulsion systems based on specific weather conditions. So from your perspective, working with tanker operators, how they are adapting their operation to accommodate these weather-related limitations? Are they modifying their routes?
Yeah, we are seeing evolution operational approaches. Initially, there was considerable hesitation from owners, operators, and charterers due to concerns around restrictions and the operational flexibility. As we know, tanker vessels are on a less fixed route of tram traders, so you never know where they are heading to in many cases. The last decade has, of course, proven that technology is safe and viable for tankers. The technology has also adapted to accommodate operational restrictions, for example, foldable, retractable, inflatable systems. The resistance to modifying established routes has changed in many cases due to the economic benefits by optimizing routes for optimal wind. And most operators are now implementing weather routing systems to adjust routing to gain the 5 to 15, 20% gains in more favorable routes and conditions. Our colleague Johan will further elaborate on this topic.
So thank you, Robert, to giving your valuable insights. So before we conclude, could you share your thoughts on how accurate performance assessment is influencing adoption decisions?
Absolutely, Aude. I mean, performance assessment has become a critical factor in the adoption decisions. Operators are increasingly demanding reliable third-party verified data on fuel savings rather than just relying on manufacturers' claims. This is not to contradict the manufacturer's claims, but just to reassure them that the data can be applied to a number of different operational variations. The ability to accurately measure, validate, predict performance across different routes, conditions is now influenced not just whether to adopt the wind propulsion, but which specific systems to choose. As we know, there is a large variety of systems applications out there. What particularly is interesting is how this performance data is being integrated into the charter agreements, with some including performance guarantees based on verified savings. This is creating a new level of transparency in the market, but it requires, of course, sophisticated assessment methodologies.
So thank you, Robert. So this will lead us to our next presentations, where Johan will provide much more details on how BV is addressing this great needs for rigorous performance validations. So welcome, Johan.
Thank you, Aude.
So in your view as advisor parts, why wind propulsion become more realistic option for shipping?
Thank you, Aude. Good morning and good afternoon, everyone. So my name is Johan Legonidec. I'm in Bureau Veritas Solutions, Marine and Offshore, and I'm very delighted to join you to discuss today wind propulsion. So let me begin by highlighting why wind propulsion merits our attention. So as you expressed with Robert, wind propulsion has evolved into a viable option for the shipping industry. This is no longer theoretical. Several vessels are already equipped with wind propulsion systems, demonstrating that this technology has moved from concept to reality. The implementation of wind propulsion, whether as primary or supplementary power source, has become a straightforward consideration for certain types of vessels and also on some given routes. For example, the transatlantic route is already very known and very considered with wind propulsion. This growing adoption is driven, as you said, by numerous technical and regulatory advantages, and it is coupled with their increasing technology maturity. So why is wind propulsion increasingly relevant to be considered in this maritime landscape? So first of all, it is obvious, but it is a cost-free energy. So it is a cost-free energy and it is clean by nature. So it offers an environmental, sustainable alternative to the conventional fuels. Then, as you already explained, and I will not remind this, but as a summary, yes, it is well considered into the regulations. For the EU regulation, for the IMO regulation, we have this wind propulsion well considered, and it brings you benefits. And as you said, for the IMO GFI, there will be also a consideration provided that it is adopted in autumn 2025. Then the other thing is really that now it becomes financially viable. It is financially viable because now you can finance these systems also through other means than your own funds, your own money. You are able to go to banks and green funds in order to finance this technology. They are prepared now to finance them. Some of these banks have taken this risk and now consider this as a business. So it is now delivered, and it is now a more attractive and lower risk investment opportunity. Finally, and it will be the last but not the least, it is a huge also lever for the fleet GHG strategy because this technology delivers substantial reductions in terms of fuel consumption, CO2 emissions, and also, as Robert was explaining, it can reduce also significantly some costs. So these tangible benefits make wind propulsion as a highly effective lever when developing your strategy. So the takeaway of this slide will be that you have here really a favorable context now to consider and use the wind propulsion.
So yeah, but why can't we simply install wind propulsion system without complex technical check first?
Yes, so it is not so simple because the wind propulsion technology influence a lot the vessel design and operations. So implementing these systems necessitates a comprehensive approach as their integration and utilization must be carefully evaluated and this across all the dimensions. As you can see on this picture, this image, wind propulsion integration affects numerous vessel areas, and it can be structure, it can be stability, it can be visibility of bridge. You will have also to manage that the system, the wind propulsion system, will give you also transverse forces, and you will have impact on your drifting of the vessel, the drift of the vessel, and also the maneuverability of the vessel. So this integration requires thorough analysis to ensure optimal performance. And what we have to have as objective is that we need to maintain the safety and the operational standards. So whether it can be a retrofit installation or a new build construction, the integration of a propulsion system will remain really specific to the vessel and tailored to the context of use of the vessel, the operating context. So as a conclusion of this slide, it is not just welding the system on the bridge. You need to assess more things and really deeply.
So we see that there is a lot of parameter interaction to consider. So which service specifically can assist shipowner in managing these technical challenges?
Yes, thank you for this question. So let's remind first that Bureau Veritas Advisory Services as delivered by Bureau Veritas Solutions, Marine and Offshore. We offer support from the first step, so the viability, feasibility stage, up to the most advanced phase, which are when the vessel when the system is installed, and you have to monitor the efficiency of is used to monitor the performance and then also possibly optimize this performance. So the first step is indeed the screening process. So when beginning the process, you need a comprehensive screening of the available options you have, which wind propulsion system you need to choose. And without delving into detailed and complex studies at this stage, because you don't have enough information, you don't have enough budget at this stage to perform this, you need, however, a solid evaluation of what is feasible, what may not suit to your operational context. So for this viability, what we can do is and I will go into the detail in the next slide, but we can screen the solution and we can perform some feasibility study, and I will explain why and how we assess this. So for this viability assessment, finally, we also work with financiers, and we provide them also with due diligence in order to check what is this vessel, how it will perform, what are the risks taken by the financiers when they finance such vessels. Then the second step and second level of support from Bureau Veritas is that we support technology developers, and we offer them to assess two things: assess and optimize their performance. So we are able to deliver some services with CFD calculations, structural assessment, and so on. And we are able to also evaluate and mitigate the risk. So for that, we delivered a lot of ASIDs workshops to assess the risk related to the design and operations. The third level of assessment is about hydro and aero performance. It is critical to really assess well what will be the performance of the hull and the superstructure in terms of aero, because without a clear model of that, you will not be able to discriminate what is the performance of the vessel. You will not be able to correctly assess and evaluate the performance of the vessel with and without the wind propulsion. So what we do, we provide hydro and aero database that are fully customized to the vessel. So for that, you have the typical calm water resistance, and we can do that with drift angles, with different drift angles. We can also consider that you have to act more with the rudder due to the wind propulsion, so it will increase also the additional resistance. So we can add different rudder angles also to this resistance. We can also provide the resistance for in-wave resistance, and finally, we need to consider also the aero resistance of the superstructure in order to know how the WASP or the wind propulsion system will be fed by the wind. Also, it is exactly the masking effects here due to the superstructure. Finally, when you have decided and you go for one given system, we can support you in the integration of such system on board the vessel. So we did some integration of such system on decks of several vessels, and here we can either propose the scantlings of this integration into the decks, or reinforcement if it is about retrofit. And indeed, fatigue and resonance can also be topics that we are dealing. And finally, perhaps, and for sure, the most interesting for ship owners will be the savings. So, depending on where you are, at which stage you are in the project, we can propose the suitable service. So forecasting is the first step. and I will explain after that. Assessing what are the actual savings. Mm-hmm. And thirdly, when you have this, how to better operate, how to optimize the use of such wind propulsion. Yes, so here, just maybe to in summary, we can support, we can bring the necessary support at all times of the project.
Yeah, it's a lot of study. But what are the first questions will the team ask when started the wind propulsion evaluation?
So the first step and the key consideration when you evaluate the wind propulsion, the first question is, can I consider wind propulsion? So is wind propulsion worth considering for my specific situation? What is the potential of wind availability, as you talked before, along my routes? What design and operational constraints I may have for this implementation? For example, typically the air draft, when you have a limitation due to some bridges that you have. So the screening and the viability is key to start and to have a quite exhaustive overview of what would be reasonable or feasible globally, but with a rougher approach. Then the second step is technical perspective. So whether for new construction or retrofitting existing vessels, the technical questions remain similar. How can we make wind propulsion technically feasible? What impact will I have on my vessel, for example, on the lightship, as you said, on my deadweight? How much can I put such systems with regards to the stability? How will my, for example, my seakeeping will be okay. And the third one is the economical aspect, the financial perspective. So really it is where the ship owners will decide, and maybe charterers and ship owners will also find agreement. The capex of the vessel with this wind propulsion will change due to the installation and adaptation of the vessel, and also the cost of the equipment. So, what is the best investment for me? What are my objectives of reducing CO2 emissions? How can I optimize the money I spent and the savings I have? What are my best solutions here? Return on investment is really key. Maybe installing 3 wind propulsion system will be more adapted than 4 to one given vessel. And some of these installations might also impact the revenue of the vessel. So if you have to install, you decrease your deadweight, or you can't load as high due to stability, or you take some space where there was some cargo, then your revenue can also be affected by this installation. So these 3 aspects really have to be looked thoroughly. So screening at first step, and technical and economic perspective at the end.
Yeah, and we see that the performance is a real key parameter. And so how can stakeholders ensure fuel savings when adopting wind propulsion?
So here we will talk about forecasting. So there are different levels of forecasting. It is essential when considering wind propulsion system. The depth and accuracy of such saving forecast will necessarily depend on the stage where you are on the project. During the initial project phase, the screening of potential solutions mainly relies on basic information provided by equipment suppliers. These assessments are typically based on a simplified approach and more or less generic vessels models. So they offer here a kind of order of magnitude for performance expectations and also costs. So this is sufficient to decide to go further, but then you will understand that you need to have more accurate figures in order to really have green light to go and to install and to make it real. So it is as the vessel design becomes more defined, more designed, then you can think about performing some detailed assessment of the specific ship and the operating conditions. Because you know all this design and all these operating conditions, then you can simulate through enhanced ship energy model. That's why we need really here a very good model, not generic, customized to the vessel, and we need here to be accurate in the process. So first step, as you can see, is again assessing and building some database for hydro and aero database. Hydro and aero, so calm water, as I explained, in wave resistance and also aero resistance. So here, by this way, you have for each condition of drifting, of speed, the resistance that the hull will have. Then, in order to convert this resistance into a consumption, you need a model, and you need not a simplified model normally, because for you need to integrate all these environmental conditions into this model and to have the machinery reacting and equilibrating for propulsive needs and for hotel load needs, equilibrating and finally determining consumptions and emissions with this profile. So how we do that? Third step is about weather routing. So here we use this as a desktop activity. We have a weather routing software at office. We simulate, let's say, 1,000 voyages from point A to point B or to point C. And then we can simulate with different parameters, some different speeds, and we can simulate, for example, a departure in the past. So in order to collect what were the environmental condition in the past, and to simulate, for example, during the 5 past years, what were the conditions on these lakes. Having that, you have positions, you are able to know, thanks to the database of the environmental conditions, what were the waves, wind, and specific and speed through water. And then this data finally will be used in the CCAT model, in the ship energy modeling that we have, in order to determine for this condition my consumptions was like that. Finally, the result. So what we have at the end, we have the results for simulations with and without wind propulsion on one given vessel. We do some routing with and without. We have a good prediction of the consumptions for each of these vessels, or each of this model in the past. And analyzing these 1,000 legs, then we are able to make an analysis and even have a sensitivity analysis or seasonality also of the savings. So, for example, in summer and winter, we clearly have seen that for some geographical area that there was indeed a change of performance for this area.
Okay, so we have forecast here the savings. But now, how to assess the actual performance versus these predictions?
Yes, this is indeed the next step, Aude. So assessing the actual savings, finally, you need to have a robust baseline reference, because otherwise you don't know to what you can compare. So it is necessary to have a good vessel without the wind propulsion, and you can compare by this way. So that's why here you can see that we use the same ship energy model built with a strong hydro-aero database and a strong vessel machinery model. Then the input will be different. This time you don't have the forecast of the routes, but you have real routes. You have the real data. So here you require reliable high frequency data coming from the vessel. There is also a good knowledge, good expertise here to clean, to know which are the valid conditions to be used, how you filter this, how you consider this, how you qualify this data is good or not good. And then doing that, you are able to say, okay, I was there in this at that time, so I can also either through this model or maybe with an anemometer, if it is considered reliable for this place, we are able to consider and to have inputs again into the ship energy model and to say, okay, you add such consumption, you add such, you should have such required power on the main engine, and finally you have less. So we are able to both estimate power savings and also consumption savings, because with this ship energy modeling, we are able to really consider also the consumptions of active systems. Yes, and maybe just the results. So you have the savings as a function of wind conditions. You can have the percentage and the analysis for this given apparent wind speed and this apparent wind angle. You have such amount of savings. Yes, and please, I was forgotten, but it is very important. You can also see our press release that was released last week with Bound for Blue, with Dreyfus Armateur and Airbus. And, it was really very interesting steps.
Yeah, it was a nice work. So once operational, I imagine that it is still possible to increase the wind propulsion savings.
Absolutely. So that's why here we have this slide. So again, we can use this model for the ship energy modeling, and then we can just use it because we developed this partnership with Adrena, and we can have an onboard weather routing, which will enable to use the ship energy model developed with the wind propulsion and to optimize the route of the vessel. So optimizing the route will mean determining the good route, but also to determine the speed management over this route, and have at the end of the day the good prediction of the fuel consumptions with this system.
So thank you, Johan. So to conclude our discussions, what final thought would you like to share?
We are currently in an extraordinary, exciting period for maritime technology. Over the 2 and 3 past years, wind propulsion has really emerged as an increasingly significant topic in the industry. There were many projects and successful implementation of both retrofitted vessels and also new construction. So Bureau Veritas Solutions offers its full support to this transformative technology. we will be delighted to hear from your needs and your upcoming projects. And finally, I would like to also thank and express my gratitude to our clients, the true pioneers of wind propulsion. So here you can see some good clients of us. The diverse ecosystem here surrounding wind propulsion is remarkably rich. You will have the equipment suppliers, you will have the ship owners, you will have charterers, you will have banks, you will have financiers, you will have green funds. So you have all this landscape that is really very, very active. And yes, I think it is just a start.
So yeah, thank you, Johan. So we have now reached the end of this webinar, so we don't have enough time to answer your question live, unfortunately. So I think that we will revert and come back to you with an answer by email. So I would like to thank all of you. Thanks, Johan. Thanks, Robert. And see you. Goodbye.
Thanks a lot for coming. Bye-bye.